in a practical way, what's the philosophy and what's the methodology behind FV3. It's not your typical finite volume dynamical core, but building in a way that we have guiding principle. And I like to mention guiding principle, not going to be able to go to every little single details. And then because I heard a lot of criticism, particularly from the convection community, I like to take this opportunity to do a critical review of the grid staggering and what we are gaining or what we are missing and how we go about and getting probably an optimal combination of existing technology. But of course, that nobody is standing still. We have to keep looking forward. But this is the state of art at this point. And then I like to use some example to highlight some of the differences in the philosophy in how you view and how you define and even to the tuning of the dynamical core, what you value most, or what's the outcome, what's the assumption. Are you assuming that if you take care of the 2 delta or if the best you could, that you would automatically guarantee that your global scale, meso scale is okay? Or shouldn't we just, first of all, make sure the global is correct, and then the meso scale is well represented, and then go down to cow scale? So that's our approach. We have a top-down approach that we don't sacrifice anything, but we value the priority is from the largest scale down to the smallest scale. That's the difference in priority, and that reflects in the tuning. And I say something about potential in the meso global unification, because I think this is very important for the nation, and it really helps streamline the development effort. Again, nobody is standing still. I believe in a football win, you have to score more.
Yeah, I know, and I think I have my...
That's very simple. That's and if you want to win the competition, you have to go develop faster. You have to improve. The model has to improve faster than the competition. You have to go fast. So, and that's one of the ways you can go faster. And I would also say at the end that the fast-paced development cycle is critical because nobody is standing still waiting for you. And we have to do things faster than the competition. And that has been my philosophy all along. We do things a little bit faster than anybody else. And that's important. Of course, you have to sacrifice a little bit along the way. Sacrifice a little bit of your personal life, for example. And I talked about some outstanding issue we currently have. Of course, it could probably be easily solved with help of the EMC. But I just like to point out some very basic big problem we have with the model we have using GFS physics. And then we talk about the performance, because with the caveat of the problems, probably not big. But then I would show the improvement that how do we make the GFS physics work for all scale, except that particular thing. And then don't go away. This is what you need to listen. So people on the phone, you don't want to go away until the bitter end. The transparent experience. I think I would show you some interesting results regarding the difference between IFS and GFS. And so you want to stay. And lastly, I'd like to talk about what can we do, what we must do to make GFS the best in the world. I sincerely believe it's doable, but some of the philosophy has to be changed. And we absolutely have to a faster pace. At this rate, I don't think we can catch them. Okay? What's finite volume about FV3? This is me and my team, and as well as other people's work in the past 20 years in this area in one single slide. So I struggled with this slide for a while, but this is my best attempt. So there are basically 5 key areas. First of all, we design the dipole from the outset, not looking at the equations that you are solving. Instead, you look at the conservation laws and how do you represent the conservation law in discrete finite volume space, or some in my previous training, it's called CFD training, it's called control volume. So how do you represent the conservation law, particularly suitable for atmosphere motion on the control volume? So, realizing that you have to also make your model practical enough. You cannot make a 5-day forecast. You have to wait 6 days to run. So you also have to be practical. So computational concern is also a very, very high priority list. So first, we figure out that we would discretize the atmosphere using the Lagrangian control volume. And you write as much as you could using governing equation, those partial differential equation, just as a guiding principle, but not trying to solve the partial differential equation itself. I think that's a key difference between FV3 and all in the world. We are not trying to solve the equations. We are trying to fulfill the first principles. Oh, of course, saying that it's easier than doing it, but this is our guiding principle. So the second one, again, physically based forward in time horizontal transport, given the vertically Lagrangian discretization. And the transport becomes just 2-dimensional. And that makes a huge difference in computational efficiency, actually also in accuracy. And because you are solving 2-dimensional problem instead of very expensive 3-dimensional problem. So it kind of kill 2 birds with 1 stone. And the key is, again, efficiency. Think about the most efficient numerical weather prediction in the world, the GFS, as well as I think GFS is also very, very efficient. And also the ECMWF, what do? Non-conservative, semi-implicit, semi-Lagrangian, 2-time level. For any finite volume dynamical core, finite volume scheme, if you have more than 2-time level, I do not see that as a physically based. Because you have to think on trajectory, on characteristics. There are only 2-time level, before and after. If you have 3-time level, I think that's more like you are solving the equation mathematically. You are treating it as an equation, as a numerics. You are not treating it as a physics problem. So that's basically the distinction. And if you keep that physical base in mind, you can reach something kind of surprising occasionally. And I will show you a very good example in number 4. But anyway, summarize, I believe in the genuine finite volume scheme, it's non-separable in space and time. So the space discretization and temporal discretization are not separable. Some center kind of claim about high order in time accuracy. I found that it's a little bit unphysical thinking, although it may be accurate in some cases, but they lost some physical consistency along the way. And then number 3 is probably a little bit more controversial choice. I actually have been telling my group the reason of my success is in Dynamical is because I do not believe in the traditional analysis. Those are not necessarily wrong, but it was kind of time of the past thing. When you move on, you use different numerical methods. Don't stick to the old thinking. Some modeling center has the kind of thinking of a birthright. They choose secrets, so they are automatically better than everybody else. This is not true. You have to work for it, even if you use the best possible choice. But what we choose is actually a little bit deeper thought, not just on surface, looking at 1-dimensional or even 2-dimensional linear analysis. Thinking about the atmosphere model is highly nonlinear. If the world is linear, then the spectral model is the perfect model. It's exact for the linear waves. So just thought about it a second. And then the final volume integration of pressure gradient force. I got this inspiration from the aircraft design that I actually took at a dynamic lesson when in my college days. And then I have been thinking about an atmosphere and the aircraft. Actually, they are interesting correlation. And then again here, it's interesting is we talk about the C and D grid staggering. And when you talk about a pressure gradient force in a three-dimensional atmosphere, the horizontal and vertical pressure gradient are not separable again. And those linear analysis it's just not meaningful at all. And I can show you an example of that. And the number 5, non-hydrostatic extension. So the hydrostatic model worked nicely with Lagrangian discretization in the vertical. The tricky part is when you heard hydrostatic. So imagine that what it does is, if you have Lagrangian discretization, the surface sitting on top of the Lagrangian surface, you don't see the mass coming in and out. But if you are sound coming up or coming from above or bottom, so that's what the hydrostatic extension is physically, that it permits sound to go through the Lagrangian interface. But in the hydrostatic case, nothing goes through, just gravity wave, sound wave, no sound wave. So that's the major difference. So this is one of the highly criticized area of the finite volume core that we have developed. I like to say that we choose this grid not randomly. we gave much deeper thought than a pure C grid or a pure B grid or a pure D grid. That I like to see it as a balanced approach. You think about, here I list 3 major things: pressure gradient, geotropic balance, and potential vorticity and helicity representation. That's nonlinear. So I give it to C grid. The pressure gradient, if you look at the diagram, the pressure gradient for the white arrow, that's a C grid. The black arrow, that's a D grid. They are orthogonal to each other, and they are actually like fire and water in the Greek and Chinese ancient philosophy. They don't like each other, but they complement each other if you can force them to work together. So, and also in a philosophical sense, it's just like yin and yang, they are opposite. And they do things entirely differently, but they have their strengths and weakness. And calling out one versus other is a little bit silly. And C grid basically requires no averaging in pressure gradient. So it's the best grid indeed for linear pressure gradient driven waves. But that's about it. Also, by however, I have to give that the transport you also need to have a C grid wind at the orthogonal to the finite volume. But D grid requires averaging in both directions for pressure gradient. So it's indeed the worst possible grid for pressure gradient. But that's given everything being equal. Now I want to say that not everything is equal here. You don't have to make it equal. So we can overcome its major weakness, maintaining its strength, by using fourth order finite volume discretization. That's an excellent property of the piecewise parabolic distribution. If you use piecewise parabolic to construct a subgrid distribution, on the surface it's not very accurate, but if you take a difference, that's the pressure gradient, it becomes fourth order accurate. So that's what we do. Now, geotropic balance is pretty obvious. That if you use C grid, you have to average in both directions. It's worse grid for geotropic balance, but D grid is the best in the sense that no averaging is required. In numerical method, the more averaging you do, the less accuracy you get. So that's one guiding principle. And you don't have to go to Arakawa analysis to know this. You just look at the discretization, and you should be able to tell. Potential vorticity and helicity representation. Potential vorticity is well known, but helicity is not as well known, or people try to avoid it because it's not good for the C grid. If you look at the C grid, helicity, the vorticity naturally defined at the corner point. The vorticity is naturally defined at the corner point here, and vorticity is defined at the center. And the vertical velocity also typically defined at the center. In every 3 it is. So vorticity and vertical vorticity and the velocity defined at the center, they naturally give a very good representation of helicity. Helicity is very a key dynamic for the storm dynamics. when I was a postdoc at the University of Oklahoma under Dr. Sleevy, to me about helicity all the time. So I do learn something from there, that you have to also take care of helicity, not just divergent component. Divergent component, you can overcome it by higher order differencing, but you cannot overcome helicity. So this shows in the simulation of supercells.
Very quickly, I'm sorry. Can you tell us what is the actual difference between a semi-staggered grid that we use in NMMB and the technique that you E-grid is basically C and D grid.
I'm sorry, I'm not going to talk about NNMP or E-grid. Or today I'm going. I'm sorry, I am really out of time, and I'm not going to comment on NNMP. But you are welcome to talk about NNMP after the presentation. So please ask questions relevant to the talk, and I can easily go over time. So I am not going to talk about NNP at all. So here's the analogy that I draw about how you treat the kind of Lagrangian and vertically arbitrary grid. Think about the aircraft design. The wing, that's a cross section over here. And this is the cross section. And you can look at the forces acting upon this aircraft. There's the control volume. And this is how it's solved in the aerodynamics. You have a lift force, and you have a drag force. So basically, you do a contour integration along this curve. Basically, you do a control volume integration along this shape, and you get a resultant vector force. It's a vector, and you decompose into vertical component and horizontal component. And vertical component give you the lift force that support the weight of the aircraft. And the horizontal actually do give you the deceleration. But in the case of a sphere, it's very similar. The next view, next graph. But you think about staying here for a while, the hydrostatic and non-hydrostatic case. The hydrostatic, you are on airplane cruising. It's basically hydrostatic. So I mean, there's no vertical acceleration. And it's basically the hydrostatic approximation. So if you integrate around the wind, the next force is the hydrostatic balance. It has to balance exactly the weight. But if you are like a fighter jet, you are now on Boeing 77, then there is a highly dynamic, non-hydrostatic, and there's vertical acceleration term. That's your vertical acceleration, what we use. So the drag mimics the du dt term, the pressure gradient. And the lift force either is the hydrostatic balance or in the hydrostatic case, it's an acceleration. So this is the kind of analogy. Keep this in mind, and versus the previous illustration, this black box here is also like the cross section of aircraft wing, but that's actually the control volume in the finite volume core. So if you look at that in this simple cross section, two-dimensional cross section, you look at it that there are only four forces acting upon the control volume. And if you think this is, if you integrate around the globe, all pressure force naturally and automatically cancel. And this is a very key property, very few model has. Is the pressure gradient itself does not produce noise. Some model produce a lot of noise. I can show you in a minute. But so what you do is we let the vertex 1, 2, 3, 4 points. So you do a contour integration. And as I just mentioned, is a sum of the vertical forces. The drag is the du by dt term. That's your pressure gradient forcing. And this is exactly what we use in FV3. And now I also have to explain that the model type and the model pattern are like naturally Lagrangian surface. So the model type is indeed an approximation. You have to cut the model type somewhere. So the assumption we make is probably less intrusive than, say, a constant height model like ARW Wolf or MPAS that has a rigid lid. They cause a lot of wave reflection. But if you have a Lagrangian surface, yes, it's not perfect at the top. Yet nothing is perfect. But it is like it actually allows vertical velocity, non-zero vertical velocity. But the only thing it doesn't allow is it's a flexible surface. So no mass can penetrate out of the model type. And the bottom surface is naturally Lagrangian surface because the bottom surface never moves, it never changes. It is a Lagrangian surface. So something people probably didn't realize, the dense surface is a Lagrangian surface. So so this is the so because there's this controversial about C and D degree, and the C degree for pressure gradient is indeed under linear condition is indeed assuming second order center differencing. That's assumption here because we don't use second order center difference. But here in this NGGPS phase 1, MPAS they use a C degree indeed is the second best here, if you can judge against the linear solution here. So that's this NNMP version degree there, and the picture speak for themselves. And MPAS certainly do reasonably well. However, if you look at the near mountain area, there's some distortion of the wave. And you compare to the FV3, there's no distortion compared to the linear solution at the bottom here. However, this is not a story. This is kind of equivalent solution. And you look at the intermediate solution here. So I plotted the 30-minute solution. They look almost the same near the source region, except in a far field, where you have noises generated from this degree discretization. And certainly it can be suppressed, but in a regional model, you really don't care about that because the noise propagated out of the domain. But what happens if there's no mean wind? And actually, there's a test that I published in 1997, Comparative Journal, Lin 1997, but it has been modified and used for the DC MIP test here. DC MIP 2012, hydrostatic equivalent test. In this case, it's almost the same as the previous mountain wave test case, but the wind is 0. So the noise do not propagate out of the domain, and that's what happens. Regional thinking versus global thinking. In this case, you are the global, and there's no escape. So your noise will accumulate like that, and I believe this is an acceptable behavior. So with that, I think that today and tomorrow we have a tutorial, and Lucas will be talking about the next degree and stretch degree a little bit. So everything all for you, the advantage of you can actually go to a global thunderstorm resolving resolution today. If you just use the existing resource, I believe it's doable. It's fast enough to be doable, but I would leave this to future work. And this is what we do in phase 1 using the GFDL physics. This is GFDL physics, not the GFS physics. And the 3-day forecast compared to the satellite visible image. I think that what I like to reemphasize, what we do is from top to the bottom. We look at the global scale first to make sure the global is correct, and before we look at the near grid scale. Sometimes that's our noise, sometimes that's true, so we don't know. But our emphasis is larger scale, the meso scale, and then the cloud scale. So we want to make sure this is done correct first. And I would actually show you some of the traditional NLP skill comparison. Variable resolution, anomaly correlation versus global uniform in a later presentation. So this gives you our down to the very bottom simulation of the very high resolution, what down to 1 kilometer. Still using the global model, down to 1 kilometer. And then you can actually start to simulate something interesting in the cloud base. And people do not believe that's tornado. Of course, I think it's not. Tornado is too big, but it's tornado-like vortices. I would turn it that way, because the model correct mechanism to simulate it. But the resolution is just too close. But important thing is, do you have the correct mechanism or not? In the 1970s, when Suki Manabe first simulated hurricane in the global model, people laughing out of the room. But today, I guess people agree that he's correct. He was presenting climate model simulation of hurricane with 200 or 400 kilometer resolution, and people laugh at him and say it's impossible. How can you simulate a hurricane using 300 kilometer resolution? Now this is the same thing happening again. Now you can laugh at me saying, well, 1 kilometer, 4 kilometer I mean, you just don't have enough resolution to simulate anything like a tornado. But I believe we have the correct dynamical and physical mechanism built into the model. It's a stretched. Yeah. It's stretched variable resolution. So I believe the point is we do have a correct mechanism to do the cloud scale. And probably a little bit better than the other approach. Because we play, I mentioned that the helicity is the key to this rotating storm.
But 1 kilometer does not resolve completely.
No, that's not. Of course. But you have to have the basic fundamental mechanism. I'm not saying we resolve it, that would be silly. But anyway, you have to have the mechanism, and there's a hope for continued improvement. So, looking at the kinetic energy spectrum, I'm starting with the global uniform resolution, 3.2 roughly, completely GFDL physics. And we start from the GFS initial condition at the bottom. Of course, it does not have the small scale. And then you see the model gradually spinning up the mesoscale and the cloud scale motion. Of course, it's not really cloud scale, but it's close enough. So hour 1, hour 3, not quite. But when we get to day 3, and this is the theoretical fit of the serial of the mesoscale spectrum minus Y3, we got an almost perfect fit, minus Y3. So this is the uniform global. What happened with the GFS resolution? And we done this in NGGPS phase 2. So this is a comparison with MPAS. And initial condition is GFS initial condition. And this is after 10 days. And all the cases coupled together. And you see again, FV3 here, it's a perfect match in the mesoscale to the mass visor. And MPAS in no place, it doesn't simulate the mass visor. And however, when you counted the noise, there are a lot of 4 delta noise simulated here. And if you count the noise, it does simulate the mass visor for some reason. But because they were trying to minimize the diffusion and using a much smaller diffusion than FV3. Intrinsically, I can argue that intrinsic numerical diffusion in FV3 is smaller than MPAS. And so in real model, we use a somewhat larger numerical diffusion than MPAS. So if you look at the 2 delta X wave, 4 delta X, 2 to 4 delta waves, they are not well simulated. MPAS seems to have more energy there, appear, but is that good? You have more noise in the 2 to 4 delta. I don't think so. So it's a difference in modeling philosophy. We want to maintain the large scale first, and the mesoscale, and the cloud scale. So the end result is, and if you look at the mesoscales, mesobeta, 20 to 200 kilometer resolution, MPAS has been repeatedly shown to have half of the energy than other model. So I don't know what that means, but it has less energy. And remember, this curve is log scale. So emphasizing at the very bottom, which has 5 or 6 order less energy than mesoscale, and you pay all the attention to the 2 to 3 kilometers, is that good for NLP? No, this is a question I think we should try to answer. So try to make GFS suitable for all scale. So we have done some preliminary development at GFDL. So the first step, we try to replace GFS cloud microphysics. That's a gel card scheme. It's a very simple yet effective scheme for NLP. And it has been doing a very good job thus far. But we like to see if we can improve upon that. And in the process, also improve the large scale. Not just improving the cloud scale at the expense of the large scale, which is something we should never do. So our priority list goes like this. We will try to work with Brett Fredia at EMC and try to get that scheme operating in our modeling system as well as in the future GFS. Because I think I failed to mention that FV3, one of the advantages, its transport is very accurate. And if you do not have an accurate transport scheme, and you put in the advanced cloud microphysics package in a model like GFS, you don't necessarily get improvement. I will show in a minute, we get very substantial substantial improvement by putting a GFDL car microphysics into the GFS framework. So I list 1, 2, 3, 4, 5 things here. You can read a year later because you are going to have my presentation. But basically, this GFDL car microphysics was designed for seasonal predictions and for climate simulation. It was not designed for NWP. So I repeat, it was not designed for NWP. However, we tuned the car microphysics from the climate perspective, looking at the global energy balance, looking at the condensate amount to see if it's reasonable or not globally. Didn't pay any attention to regional details. And let's see what happens if you only look at the global. And
I want to point out that we are also bringing microphysics here.
Wonderful. They may be similar to number 2, the universal gamma. They want to bring in a double moment microphysics. I think that what we do at GFDL, we are not proposing as a candidate, but I want to use that as the baseline because it was really not designed for NLP, and maybe something may be missing, but I like to use that as baseline. You can think about that as a low bar you have to pass. And so it's scale aware in the sense that it's finite volume thinking, actually. I coded it. This car microphysics is quite unique because it has vertical and horizontal subgrid distribution in a finite volume way. All right? It's based on first principle. I try to stay as Oyama-like as possible. So we actually consider the heat capacity of all the condensate, and in addition to water vapor, not just dry air. Most car microphysics only use CP, for example, dry air. That is wrong. And on top of that, we also consider heat and momentum transport by the falling condensate. So when you have falling rain or falling snow and grapple, it's all in the model. They do carry heat and they do carry momentum, and we consider that. So in addition to the dynamic, the so-called condensate loading effect, of course we have that. But this is associated with the falling condensate. So we added that in the car microphysics. And the other thing we do quite new, until recently, I just found out that ECMW do exactly the same thing. So it's time implicit flow of the condensate. And in terms of, it's very compatible with the initial condition from IFS. I think it's just plug right in because they almost have all the species we have except guapo. So this physics works incredibly well with ECMW IC. And in terms of complexity, it's a lot simpler than double moment, but it's a lot more complicated than ECMW car microphysics. I read their document, and it's a lot more complicated. So we sit right in between. Okay, before I show you the forecast skill, I want to show you some of the problem we have with the GFS. We're still struggling. We don't know what to do. So the albedo was enormously different than the GFS. It's shown here. It's very different from. This is diagnostic done. So this is EMC's plot. We just copied directly from the web. And the MPAS has similar problem, and they probably have even more problem for the CIs, but we also have a problem with the CIs. So I don't know, this may cause a lot of problems, but just keep this in mind. And also because we are looking at ECMWF forecast as well as their initial condition, we noticed something quite interesting, the terrain. So this is the GFS terrain that we all use similarly. And this is high resolution, minus the high resolution USGS terrain, the difference between GFS. And so there's nothing jump out of the figure. But if you look at the ECMWF, you see something interesting here. This is hugely different. Actually, when we use FV3 versus their terrain, the difference is largest 2 kilometers. And also over Amazon, this little mountain is not there in the ECMWF. I checked in the NASA space shuttle observation of they have a nice data set, and they agree with ECMWF, not with USGS. So I think something wrong with the USGS over Amazon. And the Greenland in particular, if you look at the 500 millibar high normal correlation, they may hurt you a little bit, I guess. but I don't know how much. But I just saw that it's interesting to bring this up because I found it recently, because we just started using their initial condition.
Well, they did patch the Greenland with their own data set.
Yeah. How about the Amazon? Because
John, I don't remember.
this one, if you check NASA space shuttle data, they agree with ECM.
I do remember they have replaced the Greenland topography with their own.
Yeah. Very large difference.
EC did.
The EC did.
Okay.
I think we should.
Much higher.
Anyway, this is the standard GFS physics running GFS initial condition. And the blue curve I just showed, just for convenience, I show the difference, relative skill to operational GFS. So the blue curve is all 74 cases. It's our computation. For some reason, our computed ACC is lower than yours. I don't know why, but anyway, I like you better. But anyway, this is what we computed. Is a little bit lower than yours, but
you're using the same analysis.
No, we talk about it like costing not almost the same. But we're using ERA as the truth, not the NSET.
Sorry.
All right. Anyway. So this is the original NGGPS phase 2 skill. And so after phase 2, we immediately spend 1 to 2 months tuning it, see how high can we go. Well, not too high, but at least according to this matrix, or we do something else much better. I'll show you in a minute, the precipitation, for example. But we can tune it to beat or meet GFS. But we started using the GFDL hydro microphysics. That has 6 species. It is a full-blown microphysics. There's no, it's significantly better. So kind of interesting. And so do no harm to global scale. This enables us to do the cloud scale with this cloud microphysics. But it's very encouraging to see that even the global matrix improved. But if you look at the Precipitation got even more improvement.
How much compute time you need?
This is 10 to 20% slower because we have 5 more species, and the cloud microphysics certainly is not free. So, but it's manageable. So this is the what's called fraction scale score over continental United States. Again, it's based on NGGPS, all 74 cases cover the whole year. So it's 4 seasons. And here you can see that the GFDL microphysics make a very significant improvement. So again, this is the skill as submitted to NGGPS, the original submission. It is mostly better, but not always. But once we change to the cloud microphysics, it's significantly better. And here the number is not small, 6%. That's pretty significant, I think.
Like the threat score kind of thing.
Yeah. Yes, threat score also got improved, but I don't have that part. Anyway, the other thing we want to go before we go to convection scale is if you simultaneously simulate cloud scale 3 to 4 kilometers and cover the whole globe, does that degrade your 500 millibar high ACC? I guess that's the first number you want to know. Well, the answer is no. Actually, so we have a uniform resolution here, and the stretch grid. So stretch to the in a way that over the whole United States, actually including part of Alaska. And Alaska resolution is also pretty good. It's roughly 4 kilometers. The worst resolution is over Indian Ocean, Southern Indian Ocean, something like 30 kilometers, still decent. And the model is quite affordable as well. So here show you the anomaly correlation. The conclusion, Northern Hemisphere particle counters actually is equal or better. And the Southern Hemisphere skill degraded, as you might expect, but it's 10 times faster than the global uniform resolution 3 kilometer grid. So take your poison. But it's doable. And also, I want to remind the audience here is the physics is not scale aware. And with the stretch grid, you have very large different change in resolution. So if we have make the physics scale aware as possible, we may get better. So I like to see this as kind of the baseline bar. But anyway, if you look at the counters, it's actually better, statistically significant. So this is the transparent experiment. So because I just mentioned the GFDL Microphysics is the better match to ECMWF. So we started, because we don't know what to do with the GFS initial condition, the cold condensate, we don't know where to put it. We just put it as cold water. So GFS, we have cold water, we have cold ice, we have snow, we have rainwater. The only thing we do not have is grapple, and we set grapple to 0. The other thing is interesting is the IFS has 137 level. When we first try forecast with 63, that's a mismatch. We don't get as good as the result. So we started increasing the resolution, and wow. So here you just look at the reference difference. You look at the absolute scale. This is the GFS, the bottom. And the next two are the same GFS physics, same GFS initial condition, but using GFDL, Microphysics. You get a noticeable improvement. But the biggest improvement certainly comes from the switching to IFSIC. So this is the operational European Center forecast at the time, 2015. And the
in fact, the GFS model does just as well as ECMWF model, just like that, if you use ECMWF analysis.
I agree. It's possible. Yeah, but this is what I show. I don't know how well the GFS does, but it's possible.
But you actually compare with.
No, I don't run GFS at all.
Listen, did you compare the GFS? Did you compare the FV3 when you run the GFS initial conditions from the GSI?
This is it. Are you listening? So these two are every GFS running GFS initial condition, and these are every GFS running European initial condition.
You always do better if you use ECM.
I know.
Initial condition.
Even the
Are you asking whether he did?
Yeah. So look at the difference. So here answer your question. This is running GFS initial condition. So we play very hard with GFS initial condition. And no matter what we do, the initial trajectory is set.
No, I think what Jordan is saying is that if you run GFS, the European Center initial condition, we also improve.
Okay, yeah, I agree.
Just like you are showing the here.
Yeah. I don't think that contradicts what I said.
No.
Okay.
But what I'm just saying is that there's something in their vertical structure. Their vertical structure is very rich, 137 there. So when we use 63 or 64 there, it doesn't match very well, and we actually do worse. Okay, but when we try to match, we might want to try to run the latest GFS, see what happens with their 137 there, because you get mismatch, and you may run into trouble. So maybe you can run your 128 level. That would be a better match. But anyway, I think the vertical resolution does matter, and we actually for this these are NGGPS test cases selected every 5 days, just NGGPS, and the list is growing because the computer was done. I cannot show you more cases, but we are going to have at least 32 cases. So get a little bit handle on this. But
why did you stop at 95? Could you go to 137 too?
we could try, but I have limited time and computing power, so we can try. Yeah, I think you may get better with higher resolution because it's better match. I think it's all in the condition, initial condition. After a while, it probably doesn't matter. But whether you capture the initial vertical structure or not, that's probably the key. But it somehow the high vertical structure impact the longer time. But anyway, I want to get to this point, the trajectory. Now, we perturb the GFS, you try to tune it or perturb it, whatever you call it. You cannot escape this initial trajectory. There's no cure with this initial condition. Even if you have a perfect model, I doubt you would do better. But so initial condition is really the key here. So yes, as you said that yes, you can run probably as good as them. However, you probably have to do this from time to time because I know European Center improve very fast. As I say, you want to beat the computing, you have to score quicker. They improve. They are not still waiting for us, right? So, maybe 10 years ago, what you say is correct. Right now, it's no longer true, I think. They are moving very fast. They are very impressive.
So initial condition becomes very important, which means analysis.
Of course, yeah. So,
Well, my Murthy, that analysis is very dependent on the quality of the model forecast.
Yeah, I understand.
keep things away. Okay, so there's a hope that maybe we and John and everybody can really work together, have a better simulation system. So this is what was shown in phase 2, and without tuning, the green actually produce less error globally, statistically speaking, than the operational GFS without any tuning. And this one you all know. So and this is wind, and this is temperature. So it's possible that we can improve the data assimilation if we improve the model further, as John just said.
Do you have a divergence damping in those the wind calculations and stuff?
It is. It has everything.
So what kind of damping do you have? Is uniform vertically or?
Except the top two layers, sponge layer, we call it sponge layer, they are all the same, vertically. Yeah, if you want to, you can play with vertical distribution. I think we did that before, but then again, I don't like it, so I make it a constant. Yeah, if you want to increase in the cells, yeah, you could. Yeah, normally you probably want more damping there. But in fact, stratosphere is surprisingly non-hydrostatic. I have found that even at 25 to 30 kilometers, it's very non-hydrostatic because the vertical scale height is large. And the non-hydrostatic dynamic has more impact in the stratosphere than mesosphere, surprisingly. But if you look at dynamic, it is the stratosphere is actually more non-hydrostatic. And so for hydrostatic model, you want to apply more divergence damping because that kills the gravity waves. But in the non-hydrostatic, I like rather steady the constant. But of course, this can be tunable. Anyway, this is my summary slide that I believe that non-hydrostatic model for NLP is near its useful life. Time for it to retire. For all the hydrostatic model to retire as NLP too. I really don't see any reason for hydrostatic model. Other than it's much faster. Yes, it's almost twice as fast.
Your results that anomaly correlation showed, those are with non-hydrostatic done?
Everything is non-hydrostatic. In fact, I have to say during initial phase, the hydrostatic model gives us a little bit better ACC. But the difference is so small that we forget about it. Because it's within tuning range. So I think why bother? But yes, hydrostatic could give you better skill.
So if we were to run here with non-hydrostatic, what's the overhead of the computing?
For the dynamic part, it's almost twice as fast with hydrostatic. But we compromise by using 32-bit in non-hydrostatic. So it's almost as fast as 64-bit hydrostatic. So we try to make the non-hydrostatic faster by going to 32-bit. It doesn't hurt in the non-hydrostatic. So it become equal. So GFDL, all the GFDL model running in climate mode, running in hydrostatic 64-bit. But for everything I showed today, it's non-hydrostatic 32-bit. But I like to say that the R2O to R transition. I think the way to think about it is today's NLP model could be tomorrow's climate model. I think this is the way I like to see it, and that's how you do the R2O to R. And we develop model together, and it uses a different application. But high resolution certainly is not suitable for climate at this point because we just cannot afford it. But today's NLP will be tomorrow's climate. So to be the best, I think we have to take advantage of what we already have. And I have been saying for a while that if you want to build a European center forecast, build that in the place they couldn't that's 5 to 10 kilometer range, and in the next 3 years. And that's where they couldn't adjust that rapidly. And that's a window of opportunity. And because that's where non-hydrostatic dynamic and microphysics integration is becoming very important. And they are pretty much stuck in the hydrostatic. I think they saturated their benefit of the IRS hydrostatic model. And I don't think they can get too much benefit out of increasing resolution, but we could. Transparent invariants are very valuable to me anyway. I found it kind of stimulating to find out different things and realizing, wow, they have a global analysis of snow and rainwater. I had never seen that before. And that seems to be a very useful thing for me to see personally as a global climate model developer, because we don't know what to trust. And looking at the global statistic of snow and rain kind of very revealing. And so they have been doing very well in that regard, running NWP globally with cloud microphysics, advanced cloud microphysics. And I do not think dynamics should be treated as a black box. That's a recipe for failure. And you can get it going with a black box approach, but it won't get you very far. Dynamic data assimilation and physics should be tuned together. At GFDL, we have learned the lesson of not tuning the cloud physics convection without ocean coupling, because all the tuning are wasted. Once you couple ocean, everything changed. And similar analogy could be drawn here. Maybe you can do your best tuning offline without DA or without dynamic or something. But once everything put together, I think it has to be retuned. And probably retuned as 3 ways process between the team in DA, in dynamic, and physics. And they have to spin very fast. You have to score more points than the competition and score quicker than the competition. So I think that if we do not change things fundamentally and change things as a fast-paced development, nobody's standing still, so we'll never catch up. Thank you for listening. And excuse my blunt comment.
So, DJ, what's the schedule look like from this point forward? Do we have time for some questions?